Alright everyone, and welcome back to week 4. So in this video, we're going to go and expand upon some of what we said about random variables in the last discussion. And what we're going to see is we're going to see different kinds of random variable distributions and some of the contexts that they'll show up in. So whenever we have some random variable x, it's distributed according to its population. So some of the examples of this we've seen so far are that we have the random variable x distributed according to the 6 faces on a die. So you have probability 1/6 that you'll get a 1, a 2, a 3, a 4, a 5, or a 6. We had the random variable x that was distributed based on summing together 2 die. So with probability 1 over 36, you'll get a 2, 2 over 36, you'll get a 3, 3 over 36, you'll get a 4, and so on. We could have a random variable x distributed based on a deck of cards, or heights of hockey players, or anything else really that you could imagine. And there are a handful of distributions that are very specific, well known, and have some nice properties that we can study. So the first kind of random variables are discrete random variables, and these are what we've mostly been playing with so far. So a random variable is discrete if the values that your random variable could take on are what we'll call separated. So for example, in the case of throwing a die and looking at the result, the values that you could get are 1, 2, 3, 4, 5, or 6. There's a separation in between them in that there's values in between. So you couldn't get a 1.5 or a 2 3/4. So there's space in between the values, in effect. So the values that you wind up with are discrete entities. Or if you're drawing cards, you would get a 3 of hearts, a 6 of clubs, whatever. In effect, what you could do is you could number each of the cards and you would get the same kind of thing. You would get a numbering of 1 to 52. You've got discrete values showing up there. You also have continuous random variables, and when you have a random variable that's continuous, the values that it could take on are not separated. And I say measurements here like time, height, and weight. What we've seen with height so far was really being treated as a discrete random variable. So when we were looking at heights of hockey players, everything was being rounded to the nearest centimeter. But conceivably, if you take a person, that person, if you could get exact measurement accuracy, could have a height of anywhere in between 6 foot exactly and 6'1". So you could have any number showing up in between if you had perfect measurement accuracy. And that's kind of what's assumed with continuous random variables. In the real world, nothing is truly continuous because you have finite measurement accuracy. You could maybe only measure to 10 decimal places. Well, you would then actually have separations. Your separations would be very small, but they would exist. We would still treat those variables as continuous, even though technically and formally they're not. Okay, so the first kind of random variable that we could look at is what's called a binomial random variable. And we've kind of touched on this a little bit just without actually formalizing what's going on. So suppose that our experiment that we're looking at consists of conducting n independent trials with a binary outcome. And we call each of these individual trials a Bernoulli trial. So you could imagine it as you're flipping a coin, you're throwing a die, you're drawing a card, something like that. You're shooting a bow and arrow at a target, something to that effect. So for whatever you're looking at, you have a probability of success of p, and then your probability of failure is 1 minus p. So we say that our random variable x is distributed with the binomial distribution np. So n is our number of trials, p is our probability of success. We use the tilde to go and denote that x is being distributed according to this distribution. If we're going to flip a coin 10 times and a success is defined as getting ahead, we would have a probability of success of a half, and we would say that our random variable x is going to be distributed with the binomial 10 and 0.5 distribution. And what the x is modeling is the number of successes that we get out of our n trials. Or we could say that we're going to go and throw a die 20 times, and we'll call a success getting a 3. So our probability of success there would be 1 over 6. For a discrete random variable, we have what is called a probability mass function for our random variable x, and it's just the function f of x that is going to be defined as the probability that the random variable x takes on the value little x. So suppose that our random variable x is distributed with the distribution of binomial 2 and 0.5. So in other words, we're going to flip a coin twice, and our success is going to be getting ahead. The possible outcomes that we could get are 2 heads, a head then a tails then a heads, or 2 tails. For our probability mass function, the probability that we get 0 successes, so we get 0 heads, is 1 out of 4, because in this case, all 4 of these outcomes are equally likely. The probability that we get 1 head, or 1 success, is 1/2. So we have 2 outcomes here out of 4 where we get exactly 1 head. And then finally, we get that the probability of getting 2 successes is 1/4. And in this case, the probability of getting any other number of successes is going to be 0 for obvious reasons. We could also go and do the same kind of thing, but instead of flipping our coin twice, we could flip it 3 times. And again, our probability of success is 0.5. So we have all 8 of our possible outcomes. One of them results in 0 successes, the one where we get 3 tails. So our probability of having our random variable result in 0 successes is 1 out of 8. We could also see that there are 3 outcomes that result in exactly 1 success, 3 more that get exactly 2 successes, and 1 that gets 3 successes, so one where we flip all heads. So we can also talk about what's called a cumulative mass function. So we first had a probability mass function. This one is a cumulative mass function. This one we denote with capital F, and capital F is going to be the probability that x is less than or equal to some number x. So we can also look at the cumulative mass function for our random variable x. So the probability of getting at most 0 successes is really just the probability of getting exactly 0 successes, so 1/8. The probability of getting at most 1 success is getting either 0 successes or 1, so we'll just add those two probabilities and get 4 out of 8. And similarly, we get that the probability of getting at most 2 successes is 7 out of 8, and the probability of getting at most 3 successes is 8 out of 8. So if you flip a coin 3 times, you're getting at most 3 heads, pretty clearly. Okay, we could also go and look at another binomial random variable where we're going to get a different probability of success. So suppose that we're going to go and throw a die, and we'll define a success as getting a 6, and I'll denote this with an S, and a failure then is not getting a 6, which is an F. So our probability of success here is going to be 1/6, and we would say that if we just throw the die 1 time, our random variable x is going to have the binomial 1 and 1/6 distribution. Okay, so the possible outcomes that we could get for this random variable are going to be we get a success or we get a failure. So our probability of getting 0 successes is 5 out of 6, and our probability of getting 1 success is 1/6. Well, we could also go and instead of throwing the die once, we could throw it twice. So if we throw it twice, we get 4 possible outcomes, but here the outcomes are not all equally likely. So that's one thing to keep in mind. Whereas with the coin toss, the outcomes were all equally likely. Here, we could get 2 successes, we could get a success then a fail then a success, or 2 fails. Now the probability of getting 2 fails is going to be the probability of getting a fail in the first throw times the probability of getting a fail on the second throw. So 5/6 squared. So we get 25 by 36. The probability of getting a success on one throw and getting a fail on the other is going to be the probability of getting a success on throw 1 times the probability of getting a fail on throw 2, or fail on throw 1 and success on throw 2. So we'll get 5 by 36 plus 5 by 36 to get 10 by 36 in the end. And our probability of getting 2 successes is the probability of getting a success on throw 1 times the probability of getting a success on throw 2. So 1/6 squared to get 1 by 36. So we could also go and throw our die twice instead of just throwing it once. Here what we'll get for possible outcomes is we'll get 2 successes, a success then a fail, fail then a success, or 2 fails. But here our outcomes are not all equally likely. And if we were to look at our probability mass function, we see that the probability of getting 2 fails or getting 0 successes is 25 by 36. The probability of getting exactly 1 success is 10 by 36. And the probability of getting 2 successes is 1 in 36. Right, so we can look at the reason why this would be the case. So we could define what's going on here in terms of a couple of experiments. E1 is the event of getting a success on throw 1. E2 is the event of getting a success on throw 2. Both of those events have probability 1/6, and they're independent because what happens on throw 1 doesn't impact what happens on throw 2, and vice versa. So the probability of getting 2 successes is the probability of E1 and E2, so the probability of E1 times E2. So we get 1/6 times 1/6, and we get 1 by 36. The probability of getting a success and then a fail is the probability of getting E1 and then E2 complement. So remember that E2 complement would be the event of getting a fail on throw 2. There we'll see is we get 1/6 by times 5/6, so we get 5 by 36 in the end. And we get the same kind of idea for a fail then a success. For 2 fails, we're looking at the probability of getting E1 complement and E2 complement. So we would get 5 by 6 squared for 25 by 36. If we wanted, we could go and throw our die 3 times, and then we'll get 8 possibilities. So the set of outcomes looks very, very similar to what we had with flipping a coin 3 times. The difference here is, again, the outcomes aren't equally likely. So the probability of getting 0 successes if you throw the die only 3 times is 125 out of 216, so a little bit above 50%. The next most common outcome is getting exactly 1 success, which you'll get 75 out of 216. Then we could get exactly 2 successes, which will have probability 15 by 216. And lastly, the probability of getting 3 successes out of 3 throws is 1 by 216. So we get it for very much the same reason. We could go in, instead of having 2 events, we would have 3 events. So we'd have E1, E2, E3, and they would just be the event of getting a success on throw 1, 2, and 3 respectively. And if we did that, we could see that the probability of getting success on each of the 3 throws is the probability of getting E1 and E2 and E3. All the events are independent, so we'll multiply out the probabilities and get 1 by 6 cubed, which is 1 by 216. And then we could do the same kind of thing for the other possibilities. And what we'd see is we get the same kind of chart that we had from before, and what we would do is just all of the places where we have 1 success, we would add up those probabilities. So what we see is there's 1 outcome here that results in 1 success. It has probability 25 by 216. We have 2 more events, or we have 2 more outcomes that result in exactly 1 success. Again, probability 25 by 216. And when we add those 3 possibilities up, we see the 75 by 216. So some properties for the binomial random variable where we're conducting n trials with a probability of success of p. The expected value for this random variable is going to be n times p. This makes a lot of sense. If you have a probability of success of p and you conduct n trials, you would figure, well, you'll get n times p successes. We could find the variance to be n times p times the quantity 1 minus p. And we could also go and find the probability mass function for a binomial random variable pretty nicely. So the probability mass function, f of x, is going to be n choose x times p to the x times 1 minus p to the n minus x. So for example, when we were just looking at throwing our die and looking at the successes where a success was a 6 comes up, when we were looking at f of 1, so the outcome where we get exactly one success, you could think about it as we have three possibilities, and we have one success in those three possibilities. Well, there are three choices of where we're going to put the success. So that's where the n choose x is coming from. If we had 8 trials and 3 successes, there would be 8 choose 3 places for where to put the successes. And then each success is coming with probability p. So we've got, in this case, 1 success with probability p, and we've got 2 fails with probability 1 minus p. So that's where each of the pieces are going to come from. Okay, a second random variable type that we could look at is what's called a Poisson random variable. So Poisson random variables, there's a parameter there that is lambda, and that's going to describe the average. So a Poisson random variable is going to describe the number of times that some event occurs over a time interval, where the average number of times that your event occurs is given by lambda. So for example, you could be looking at the number of hurricanes in a year, the number of likes or shares that you get on a post on some social media account, or maybe the number of ice cream cones that you sell in the summer. So some of the properties that a Poisson random variable has is that the expected value and the variance are going to be this parameter lambda, and the probability mass function is given by lambda to the x times e to the minus lambda all over x factorial, where x is going to be your number of occurrences that occur in your time interval. The way that we get this probability mass function is much more esoteric than the binomial one, so I'm not going to go through how we come up with this. But we can move on to going and looking at an example. So suppose we want to look at the average number of goals that are scored in a hockey game, and we're told that the average is going to be 6. So this would be a case where we could use the Poisson random variable to go and model the average number of goals in a game. So we could just go and look at some of the probabilities that show up. So we could see that the probability that there are 0 goals in the game is about 0.25%. The probability of getting 1 goal in the game is about 1.5%. And then the probability of getting 5 or 6 goals is just a little bit over 16%. The probability of getting 7 goals is a bit under 14%. And the probability of getting 10 goals in a game is about 4%. The next distribution that we could look at is what's called the geometric distribution. So the geometric distribution is modeling the number of failures before a single success. So if you remember the movie National Treasure from about 10 or so years ago, Nick Cage's character is looking to steal the Declaration of Independence. One of the quotes he gives is from Thomas Edison, and Edison was saying, "I didn't fail to make a light bulb. I just found 2,000 ways to not make a light bulb." And that's kind of the same way here. So the geometric idea here would be we had 2,000 failures before getting a single success of a practical working light bulb. So for a geometric distribution, we would have the expected value is going to be 1 minus p over p. The variance is 1 minus p over p squared. And the probability mass function, so the number of failures that we get before the first success, is going to be given by 1 minus p raised to the x times p. So this kind of makes sense because what we'd have is we would have x failures, so we would have failure 1, which occurs with probability 1 minus p, times failure 2, which occurs with probability 1 minus p, and so on. And then finally times our one success, which occurs with probability p. The cumulative mass function is also pretty nice for geometric distribution, and that's just going to be 1 minus the quantity 1 minus p to the x plus 1. Okay, so one example of a geometric distribution. There was a basketball player who played in the 70s named Rick Barry, and he was a very good free throw shooter. His career free throw percentage was 90%. And if you've never actually seen Rick Barry shoot a free throw, it's worth looking it up on YouTube because Rick Barry would shoot free throws underhanded. So what we're going to do here is we're going to go and look at the geometric distribution of number of shots made before he misses a free throw. So in this case, we're taking the kind of paradoxical definition that a success is a missed free throw. So in this case, our random variable x will be modeled by the geometric distribution with probability of success, where success is missing a free throw, of 0.1. So the probability that we have 0 failures, in other words, we have 0 made free throws before missing our first one, is 10%. The probability that we get 1 made free throw before a miss is 9%. The probability that we get 2 makes before a miss is 8.1%. The probability that we get 3 makes before a miss is 7.29%, and so on. So I've included the probability that we get 9 makes before a miss on the 10th shot, which is just under 4%. The probability that he makes 19 free throws in a row and then the first miss comes on the 20th attempt is a little bit over 1%. And for interest, I just went and included the probability that Rick Barry would make 99 free throws in a row before finally missing on that 100th attempt. And you would think this would be basically 0, but it's only about 3 in 100,000. So still pretty small, but not totally inconceivable. Okay, the next distribution that I want to look at is what's called the hypergeometric distribution. And even though the name sounds similar to the geometric distribution, they actually don't really have anything in common at all. So suppose that I tell you that we have a vase with 100 marbles in it, 20 of them are blue, 80 of them are red. We're going to reach into the vase and grab out 5 marbles at random, and we want to know what the probability is that 2 of the marbles we pick are blue. Well, so let's look at the event that we're going to grab 2 blue marbles from a draw of 5, and we're doing this without replacement, from our vase. So if we were to just number off all of the marbles to make it easier to figure out how many distinct possibilities there are, we would see that there are 100 choose 5 possible outcomes for drawing 5 marbles without replacement from our vase of 100 marbles. And if we're looking at all of the blue marbles on their own, there are 20 choose 2 ways to draw 2 blue marbles from our set of 20. And independent from that, there are 80 choose 3 possibilities to draw 3 red marbles. So what that will tell us is that the probability of drawing 2 red marbles out of a sample of 5 total marbles from our vase is 20 choose 2 times 80 choose 3, all divided by the total number of 5 marble draws, which is 100 choose 5. So in general, for our hypergeometric distribution, we're going to let capital N be the total population size. For us, that was 100. We'll let capital K be the total number of successes. So for our case, that was 20. We'll let little n be the number of draws. So how many things are getting taken out of the population. For us, that was just 5. Then we'd say that x is distributed with the hypergeometric distribution capital N, capital K, lowercase n, and our probability mass function, so just the probability that our random variable has the value x, is going to be k choose x times n minus k choose little n minus x, all divided by capital N choose little n. And that's exactly what we just saw. We would have been looking at the hypergeometric distribution 100, 20, and 5, and for the probability that x was 2, we would have gotten the exact result that we just had. So 20 choose 2 times 80 choose 3 divided by 100 choose 5. Okay, so we can now move on from talking about discrete random variables to talking about continuous random variables. So when we were looking at a discrete random variable, we'd be looking at all of the distinct values. So we could look at the probability mass function where f of x is going to be the probability that our random variable takes on the value x. We're not really going to be able to do this for continuous random variables, and we'll see why in just a moment. So instead of looking at the distinct values, we'll look at what's called the density for our random variable at a point x. Okay, so one example of a continuous random variable is what's called a uniform random variable. So what we'd like to do is come up with a random variable x where we say that every possibility in between 0 and 1 is equally likely. So if we want to come up with a probability distribution to say that every value in between 0 and 1 is equally likely, what's the probability that x is equal to exactly 0.5? Well, let's just for the moment say that the probability that x is equal to exactly 0.5 is denoted by some number c. But then because every value in between 0.5 is going to be equally likely, that means for every x value in between 0 and 1, the probability that our random variable x takes on this value x is also c. The problem that we're going to encounter is that there's an infinite number of values between 0 and 1, so if we say that c is some number that's bigger than 0, that means that we'd be summing up an infinite number of things, and if you sum up an infinite number of fixed constants, so in this case, suppose you said your probability was 1 over a million. You sum up 1 over a million an infinite number of times, you get an infinite value. That's not good. We need our probability distribution to sum up to 1. So for a continuous random variable, what's going to happen is that we're going to say the probability of drawing any single value is 0. So let's suppose that you had perfect ability to measure time, and you said you thought that it was equally likely that it would take you between an hour and an hour and a half to get from Hamilton to Toronto by the highway. What we're saying is that you could show up from Hamilton to Toronto, it could take you exactly 1 hour and 15 minutes. It could take you exactly 1 hour, 15 minutes, and 1 second. It could take you exactly 1 hour, 15 minutes, and 1/10 of a second, 1 hour, 15 minutes, and 1/100th of a second, and so on. There's an infinite number of possibilities, and if you assign a non-zero probability to any one of those actual events, and you say that all outcomes are equally likely, you're assigning this non-zero probability to all of the events, and you're going to wind up with a big problem. So we'll just say the probability of showing up at any exact value is 0. So this might seem like a really strange kind of random variable to talk about, because especially when we think about things in terms of the discrete random variable, this doesn't really make sense. But what we can do instead is look at a density for this random variable. So what I'm going to do here is I'm going to say that the density for any value in between 0 and 1 is going to be exactly 1. And then for any value outside the interval 0 to 1, my density will be 0. So we'll call f a probability density function for a continuous random variable, and it'll have a couple of properties. The first is that the function will always be at least 0, and 2 is that the total area over the entire real number line is going to be 1. Notationally, we would write this as the integral from minus infinity to infinity of f of x dx is equal to 1. If you're interested in the calculus aspect behind statistics and probability, that's what we're doing. As the textbook says, we're going to be doing things without calculus, so that's about as much calculus as we're going to see. But I just want to include it for kind of formal completeness of what we're doing. But what we usually do when looking at continuous random variables is we talk about the probability that our random variable x is going to be inside some interval. So we'd say that the probability that x is going to be between a and b is going to be the area of f of x from a to b. So again, using the integral notation for calculus, the probability that x would be in between a and b is the integral from a to b of f of x dx. So let's come back to the example where we try and come up with a way to say that every value in between 0 and 1 is equally likely. Well, we could look at the probability that we pick an equally likely value in between 0.3 and 0.45. Intuitively, we're taking up 15% of the values, so it makes sense that the probability here is going to be 15%. But another way to look at this is we have a rectangle with area 1. Our rectangle has height 1, it has base 1, so area 1, which is great because that's exactly what we want a probability density function to have. This gray slice has 15% of the area of our entire rectangle because it has base 0.15 and height 1. So that's really what's going on with probability density functions, is we just look at the proportion of area that we're taking up here. And in this case, 15% is between 0.3 and 0.45, So if we say that we could randomly choose any value in between 0 and 1, the probability that the randomly chosen value will fall between 0.3 and 0.45 is 15%. Similarly to the cumulative mass function from discrete random variables, there's the cumulative density function for a continuous random variable. And it's very much the same. Its capital F is going to be given by the probability that x is less than or equal to the value little x. So what this tells us by implication is that the probability that our random variable x is in between some values a and b is the difference in the cumulative area between a and b. So if we take all of the area that's to the left of b and we subtract off all of the area that's to the left of a, that gives us the area that's in between b and a, or the probability that a is going to be in between a and b, or the probability that our random variable x results in a value that's in between a and b. For a discrete random variable, we know that we could take the sum of x times the probability that the random variable takes on the value x for all unique values x, and our variance is similarly defined as the sum of the x minus expected value of x all squared times the probability for all of our unique values. For continuous random variables, it's slightly different. The expected value and the variance both come from integrals. We're not going to have to find them, but this is where they're coming from. So instead of summing over values, we take integrals. So first, we can take the uniform distribution A and B. So this is what we've just been talking about. What we're saying here is that all of the values in between A and B are equally likely. For a uniform random variable, our probability density function is going to be 1 over B minus A. So in other words, we'll get a rectangle where in between A and B, our rectangle is going to have height 1 over B minus A, and if you fall outside the range A to B, the probability density function is going to be 0. Our cumulative density function is going to maybe be kind of straightforward. So if we take a value that's to the left of A, we've had no area show up so far because the function was always 0 over there. So it'll just be 0 to the left of A. When you get a value that's in between A and B, the probability density function will be given by x minus a over b minus a. So in other words, it's going to start at 0 and linearly increase up to 1 by the time you get to b. And if you pick some value that's to the right of b, well, all of your area was in between a and b, so the cumulative density there would just be 1. So if we went back to our example here, all of our areas in this range between 0 and 1. So if you want the cumulative density at 2, well, all of the areas to the left of 2, so the cumulative density at 2 is just 1. Our expected value for a uniform random variable is just a plus b over 2, so that'd be the midpoint of the interval. Again, kind of intuitive. The variance for a uniform random variable would be b minus a all squared over 12. This one's a consequence of integrals, so we're just going to leave it there. The final distribution that I want to talk about here is going to be the exponential distribution. This is kind of similar to a Poisson distribution, except it's for continuous values. So for Poisson, you only have the discrete values, so like we had with goals in a hockey game, you wind up with 0, 1, 2, 3, etc. for the Poisson distribution. Exponential is very similar, but it allows for continuous values. So the exponential distribution is usually thought of as time in between events. So sometimes it could be the time to failure of a device. So maybe how long your car battery will last, you could model with an exponential distribution. Or maybe you're in a store and you want to model the time that it'll take between customers. So depending upon the context of the store, maybe you want to do work in between customers and you want to see how much work typically you could expect to get done on something else between when a customer 1 shows up and leaves and the second customer shows up. Or maybe you're interested in something like the time between hurricanes. You could also model You could also model that with an exponential distribution. And the exponential distribution has some nice properties. So one is that the expected value for a random variable x that is distributed with an exponential distribution with parameter lambda is going to be 1 over lambda, and the variance will be 1 over lambda squared. We could find that the probability density function is going to be lambda times e to the minus lambda x, where x is going to be some value bigger than or equal to 0. And if you picked a value that's negative, the probability density function would just be 0. And the cumulative density function, capital F, is going to be given by 1 minus e to the minus lambda x, where again, x is going to be some value that's at least 0. Okay, so now what I'm going to do is I'm going to go open up R, and we're going to go play around with some of these different distributions in R and see some of the function commands that you can use to work with these distributions on your own. Okay, so the first thing to keep in mind is the functions that we're going to use. So there are 4 prefixes to these functions, and then there's the root. So the root is the probability distribution that you're using. So for example, if you're using a binomial random variable, your root would be binom, and then you stick one of 4 letters at the beginning of it, either a D, a P, a Q, or an R. So what we can see here is that one of the functions I'm using is dbinom. So what that will do is that'll give me the probability mass function for a binomial random variable with prescribed n and p for some various values. The other one that I'm going to use here today is going to be p, so I could have pbinom as I have here. The other 2 functions would be qbinom and rbinom, and related for other probability distributions. We're not going to use either of those today. We might use them later, but I'm not sure offhand at the moment. Okay, so the first thing that I'm going to go and do is I'm going to go and define n to be 2 and p to be a half. So that's the equivalent of saying that we're going to flip a coin twice, and the probability that a heads comes up is 50%. So the x values that we're going to look at are going to be the sequence going from 0 to 2, or I guess n. So x val is going to be 0, 1, and 2. So we're looking at the outcomes where we get 0 out of 2 heads, 1 out of 2 heads, and 2 out of 2 heads. Okay, so then we have our list of probabilities. So the probability of getting 0 heads is going to be 25%, the probability of getting exactly 1 head is 50%, and the probability of getting 2 heads is also 25%. So that corresponds very, very nicely to what we said in the video. Then we could also look at the cumulative mass function. So we'd get that by doing our cumulative sum for the dbinom values. And what that would say is that the probability of getting at most 0 heads is 25%. You're getting 0 heads. The probability of getting at most 1 head, so you're either getting 0 head or 1 head, is going to be 75%. So the 25% from 0, the 50 from 1. And lastly, the probability of getting at most 2 heads is going to be 1, because that's all of the options. And we could, instead of using the cumulative sum function on dbinom, just called pbinom. And there we see we get 25%, 75%, and 1%. Okay, and then we could also go and look at the expected value for our random variable. So what we'll do is we'll go and set EV, so our expected value, to be the sum of our x values times the probability that each of the x values appears. So in this case, we'll get 1, which is exactly what we said we should get for a binomial random variable. We said that we should get n times p. Here n is 2, p is 1 over 2, so we unsurprisingly get 1. What we're getting is 0 times the probability that 0 appears, plus 1 times the probability that 1 appears, plus 2 times the probability that 2 appears. And that's 1. So the other thing that we could do is go and see what our variance is. Our variance here is going to be a half, and we said that for a binomial random variable, The variance is n times p times 1 minus p, and that is a half. Okay, so we could look at another binomial random variable, and this one's going to correspond to the example where we threw a die and we wanted to see, and we took a success to be the die coming up with a 6. So our probability of a success in that case is going to be 1 over 6. Our x values are going to, in this case, go from 0 to 3 because we're throwing a die 3 times. So we could get 0 sixes, 1 6, 2 6, or 3 sixes. Our probability values are going to be, as we said in the video, it's just here they're in decimal form. So we said that the probability of getting all 3 successes is going to be 1 out of 216, which is the last value. The probability of getting exactly 2 successes out of 3 is going to be 15 by 216, which is our second value. The probability of getting exactly 1 6 to show up is 75 by 216. So the first value, or I guess the second value in the list. And the probability of getting no successes, we said, was 125 by 216. So what we see is that all of the probabilities that we said from the video line up exactly with what we get. Okay, and then we could do the same kind of thing. We could see that the cumulative sum and the p-binom function are going to return the same thing. So the probability of getting at most 1 success is going to be about 92.5%. The probability of getting at most 2 successes is going to be about 99.5%, and then the probability of getting at most 3 successes is 1. Okay, and then we can do the same kind of thing where we're going to go and calculate our expected value and variance. So what we see is that our expected value is 0.5. Again, that makes a lot of sense because we said that we're going to do 3 trials and our probability of success is 1/6. So you'd expect to get a half success. In other words, if you did this kind of experiment a whole bunch of times, so you rolled 3 die and you counted the number of times that you saw a 6, and you did that experiment a whole bunch, and you averaged that, you would see that your average comes out to be about a half. And our variance here is going to be about 0.42. So that'll be the n times p times 1 minus p, and we get the exact same value. Okay, so then we can look at the Poisson random variable. So with this one, this is going to be where we had the example of modeling the number of goals scored in a hockey game. So we said there our average value was 6 for lambda. To get the probability for in this case, a number of goals to be scored in a game, we would call d pois and pass the lambda parameter. So with d-binom, there were 2 parameters that we need to give, the n and the p. Here, a Poisson distribution just has the 1 parameter lambda, and we see that the probabilities are exactly what we would expect based on the results from the video. So we get that the probability of 0 goals being scored is about 0.2%. The probability of 1 goal being scored is about 1.5%, and so on. And the probability of you getting 10 goals scored is about 4%. Okay, so then we can also calculate our expected value and variance as before. So here, one of the things to keep in mind is that a Poisson random variable, you could theoretically get any value showing up. So there is a possibility that 200 goals get scored in a given hockey game. Something negligibly small, so you're getting 1 times 10 to the minus 222. So imagine a 0, a decimal place, 221 zeros, and then a 1. So something ridiculously small, but not 0 actually. Okay, so then our expected value, as before, will be all of the x values times the probability that they appear. And our expected value here, we said that for a Poisson random variable, the expected value is just lambda. So we'd better get 6, and we get 6. We also said that the variance is lambda, and we see that the variance here is also lambda for 6. Okay, so now let's go on to the geometric distribution. So there we were looking at the probability of Rick Barry missing a free throw. So we said that our probability of success was 10%, so the missed free throw is 10%. We'll do the same kind of thing. We'll take our x values to go from 0 to 200. The reason why I'm picking 0 to 200 is just because after a while the probabilities are basically 0. So this is sort of summing over an infinite number of outcomes, but we're just kind of truncating it once the probabilities get too small to kind of be relevant. Okay, so then our probability values are going to be given by dgeom, and our expected value will be 9, and we said that for a geometric random variable, our expected value is 1 minus p over p. So what this would say is that if you've got Rick Barry shooting free throws, you would expect him to make 9 free throws before missing the 10th. If you were to go and conduct a bunch of experiments where he would go and shoot free throws until missing, so say you did that 10,000 times, what you would see is that if you average the number of made free throws before a miss, it would average out to 9. And then we could calculate our variance, which is going to be about 90. So what we said for the variance for geometric random variables, it should be 1 over p times p squared. So here, the reason why we aren't getting exactly 90 is because there's still a little bit of the variance that I'm missing by only going from 0 to 200. If I went from 0 to 1,000, we would see that we should get 90 exactly for our sum. Yeah, there. So when we take a few more values, we go and cover off the little bit of variance that was being lost. Because again, really to find the exact variance, we're supposed to sum up over all possible outcomes. And as I showed in the video, there's about I think 3 in 100,000 chance that you'd wind up getting 99 made shots before a miss. Yeah, so about 3 in 100,000. So small, but not completely unheard of. Okay, so then the next thing that we could do is look at the hypergeometric distribution. So one thing to keep in mind here is that R defines the hypergeometric distribution differently than I did in the video. So in the video, I define a hypergeometric distribution based on the total number of marbles, the number of success marbles, so in our case the number of blue marbles, and then the number of marbles drawn. R defines the hypergeometric distribution in terms of the number of success marbles, so for our case 20, the number of failure marbles, so that would be the 80 red marbles, and then the number that are drawn. So you just want to keep that in mind. If you ever need some guidance with something, you can call help and whatever you're looking at. So in our case, if we wanted to see what's going on with the hypergeometric distribution, we could call help of d hyper. And it'll pop out this little window, and it says we could go and call d hyper, where we give a value x, m, n, and k. X is going to be our value, so from what we did, 2. M is the number of white balls, so white is taken as the success. N is the number of black balls, so those are the failures. From what we did, we had blue and red instead of white and black. And K is the number of balls that are drawn. So for our case, that was 5. Okay. So what we can do is we can say that we had 20 blue marbles, we had 80 red marbles, and we took out 5. And what is the probability that we take out 5 marbles and we get exactly 2 blue ones? About 20%. And what we said is that this probability is 20 choose 2 times 80 choose 3, all divided by 100 choose 5. So we could just verify that we found the correct thing by using the choose command in R. So choose. So we're looking at n choose k, so we choose 2 marbles from a set of 20 blue marbles. And what we see is that the probabilities all line up very nicely. Okay, so that covers the examples that we did for the discrete random variables. Now we can go and look at the continuous ones. So the first one that we did was we looked at the uniform distribution over the interval 0 to 1. So the same kind of thing works as before. We can call dunif on some values. They'll give us the probability density function values at the various points. So this is going to ask for the probability density values for a uniform random variable, for the uniform 0, 1 random variable, and we're looking for the values -2, -1, 0, 1, and 2. And what we see is that the probabilities are 0 at -2, 0 at -1, 1 at 0, 1 at 1, and 0 at 2. And that aligns very nicely with what we said in the video. For the uniform 0, 1 variable, the probability density function for any value in between 0 and 1 is going to be 1, and 0 for any value outside of the 0, 1 interval. We could also go and call dunif on any other value in between 0 and 1, like a half. We would see that the probability density function is going to be 1 at a half as well, because it's inside that 0 to 1 interval. If we call dunif on 44 for our 0, 1 random variable, we'd get 0 because 44 is outside of the 0, 1 interval. punif will go and give us the probability of getting a value that is at most a half. So for us, what we said is that's the same thing as saying what proportion of all of the area is to the left of 1/2. And for the uniform 0, 1 random variable, half of the area is to the left of 0.5, and 3/4 is to the left of 0.75. We also asked, what is the probability if x is a uniform 0, 1 random variable that x lies in between 0.3 and 0.45? We said that we could just look at the amount of area that's to the left of 0.45 and then subtract off the amount of area to the left of 0.3, and that would give us the area in between 0.3 and 0.45, and we get 0.15 here, which is exactly what we said. That interval between 0.3 and 0.45 gives us 15% of the area. Okay, and then we could also call a plot here to just go and plot our density function. So this gives us a plot of the density function for the uniform 0, 0, 1 random variable. What we see is that outside of the interval 0 to 1, the density function is going to be 0, and in between 0 and 1, the density function evaluates to 1. We could, instead of looking at the probability density function, look at the cumulative density function. And what we'd see is the same kind of behavior that we would expect. There is 0 area to the left of 0, and once you hit 1 and go to some value that's even bigger than 1, you've had all of the area from your probability density function to the left of that, so you get a cumulative density function for value for 1 for anything that's 1 or greater. And in between 0 and 1, you just get the line y equals x. And then we could verify what we said about the expected value and the variance. So what I'm doing here is I'm just shortcutting some of the calculus stuff. What this command is doing is it's saying that we're going to integrate the function x times the density at x for the uniform AB variable where a and b are 0 and 1, and we're going to do this integration from 0 to 1. So we're just going to get all of the area in between 0 and 1. And what we see here is that we get 0.5, and then it also has an absolute error just because calculating the integral is done numerically, so there's an error associated with what's going on. Kind of similar to what I had with the variance a moment ago, where I wasn't getting exactly 90, I was getting something very close to 90. Same kind of idea here. And this makes sense because what we said is that the expected value for a uniform 0, 1 random variable is going to be a plus b over 2. Here we'd get 0 plus 1 over 2 for a half. Then we could calculate the variance very similarly. So we said that the variance is just going to be x minus the expected value squared times the density at each of these values x, and we do the integral over the interval 0 to 1 here. And what we get is 0.83 with the 3's repeating. And what we said is that the variance for a uniform random variable is going to be b minus a squared all over 12, which is 0.08 with 3's repeating. Okay, and then the last thing that we're going to do quickly is just look at the exponential distribution. So I didn't do an example of an exponential distribution, but I'm just going to go and show that the variance and the expected value are what we think they are. So I'll take lambda to be 7, so that's my rate for my exponential distribution. We said that for an exponential random variable, the expected value is going to be 1 over lambda, so in our case we want 1 over 7. I'm going to do the integral from 0 to 100. If I do it for any more, R runs into some weird numerical issues. But what we get is 1 over 7 here. If we start going bigger, eventually, yeah, what we see is that once we go up to 10,000, R is trying to tell me that the expected value is going to be 0. The issue there is that there's numerical round-off issues that R is having. So this is also one thing to keep in mind when using computers, is that if you get an answer that doesn't make any sense at all, it could be that you've actually done everything right. The problem is with the computer. Those are kind of a hassle because usually when you get an answer you don't expect, the natural inclination is to think that you've done something wrong. It could be the computer. So we can also go and see the variance for an exponential random variable. So here we expect to get 1 over 7 squared, and we get 1 over 49, which is exactly what we would think. Okay, so that gives us a good overview of a lot of the probability functions that R has at our disposal that we're going to use a little bit going forward, and you could even use when thinking about what you want to do for your project. Okay, and I will see you in the next video.